Are we on? Because I think we might need to
Yep.
press it. Okay. We haven't pressed the red button yet, I don't think. My bad. I saw the red light.
I think we're in the right mode.
Is there any picture?
Yeah.
Can you see me?
We can see you.
Okay.
Yeah.
Hi, people. Okay. So we're going to do a partial fractions breakdown. This is our favorite kind. It's the simplest kind. There's no worries. Everybody has done this. You did it in pre-calc. You didn't know why. And your teacher couldn't tell you.
Yeah.
Because you didn't do it again until Calc 2, and now you realize you did it so you could integrate. So what did we do? We said, first of all, let's multiply through by a common denominator. And I'm going to show you where to take the shortcuts, by the way. But I want to remind, because not everybody learns it the same way. Okay? Do you all agree that these are equal? So now what I want to do is equate numerators. So I have 1 equals a, x plus 2 plus b, x minus 3. So the first step I want you to skip is this one. If I put all these over a common denominator, the next thing is to equate numerators. Just go right from here to here. A lot of folks don't realize you can do that because it feels like you're cheating. You can't do this without equating numerators. So I go, okay, this, okay, boom. Now, the formal way in every math book is to now gather variables. This is absolutely correct. And then it's called equating coefficients again. I don't have an x term, therefore a plus b must be 0, and 2a minus 3b, oops, sorry, that's awful. 2a minus 3b is what?
1.
And this is absolute correct mathematics. I have 2 equations, I have 2 unknowns I will solve. Where this gets dicey is, what if I have several linear factors? What if I have 4 linear factors? Now I have 4 variables and 4 equations, and if you don't know linear algebra, you're not solving that one algebraically. You're not solving that one without a matrix. Sorry. I'll give you a month, but no, you're not going to solve that without a matrix. But wait a minute, I have 2 equations and 2 variables no matter what I do. So there is a much, much easier way. This is absolutely correct. This is how most people learned it. It's not what I show people. No. Pick any 2 real numbers for x, and you're going to get 2 equations and 2 variables. Anybody have a good idea what would be really good choices to start with?
-2.
How about -2 and
3.
+3? Okay, if I choose -2, then the left side's a 1, and the right side is -5b, which means that b equals -1/5. If I choose 3, then the left side is 1, and the right side is 5a, which means that a is 1/5. That's it. That's what I do. How many learned that version, by the way? Yeah, and by the way, there was a time when it used to be every hand went up. Now it's less and less and less. Never do it by setting up systems of equations. Never do it that way. It's not wrong. It's the absolute most amount of work you could humanly do in the problem to get to the same result. Your goal is to get these 2 numbers. Don't make it hard. If I had 10 linear factors, this is still this easy. It wouldn't matter how many I have. It's still 1 step because I'm choosing values that make every term but 1 0. That's it. So now I go back to here and say, okay, this was, and I'm going to pull the 1/5 out in front, just makes it easier then. And I have 1 over x minus 3 minus 1 over x plus 2. Now that's a very, very simple antiderivative. This is why you learned integration using partial fractions decomposition in Calc 2, because it comes up in integrations. Okay? The irreducible quadratic, I'm not even going to bother with right now because it just doesn't come up all that often for what we're going to do, but that's an irreducible quadratic is one that only has imaginary roots, like x squared plus 5, right? Everything can be factored, but we only want things that have real roots, okay? So linear or irreducible quadratics. The complicated one is the repeated root, and we're not going to get to that one until late in the course. We're going to look at that problem, but it comes up in a different context. It doesn't come up in integration. It actually comes up separately. But we'll have things that we need to pull apart. So we're going to do problems that basically have this. So we want to remind ourselves what the mathematics was because we don't want to be stumped because the numbers won't always be friendly. So the spread of a rumor, all right? I'll keep it really simple. There are n people in an enclosed environment. That just simply means you can't leave. And no one else is coming in. One person is walking in that has the rumor or the virus. Now, I'm that person. And I go up to you and go, eyes get all bright. So then you turn to him, and then, by the way, I keep going. And then you guys turn and you keep going. So what happens? It's wildfire. We will only assume one thing, that we're going to tell people at kind of a constant rate. I'm not going to tell you wait 5 minutes, tell you wait 30 seconds and tell you. If I wait 5 minutes, I'm going to wait 5 minutes every time. Not that that's an absolute rule, but it makes it impossible to control the equation. We'll just simply say we're going to do it at the same time. Now, I'm going to go tell you the room you. I already know it. Oh, okay. I already know it. Will there be a time when you guys are answering, I already know it? Yeah. Maybe there's one person left in the back of the room and they're sleeping. They didn't even know the room. So what's happening is we're massively telling people, and then it's going to slow down. So graphically, it actually looks like this. This is nobody knows. This is everybody knows. It actually goes like this. The reason I'm drawing this graph is this graph is actually very common in other areas. And I find it interesting. I looked it up because I'd seen it before outside of calculus. Fish in a river, fish in a stream. We have an area that's been overfished. So what do we often do? We'll put fish out there. Maybe trout, maybe salmon. What happens? They start multiplying. Can they multiply forever? No. What will happen? At some point, well, no, there's a river. They're not going to run out of room, but at some point they will stop multiplying because it's crowded. I'm swimming around, I'm bumping into you, I'm not going to have any more babies. Okay. The fish in the stream actually follow this. This would be the upper limit of what the stream can handle, but different than the bacteria in the petri dish. I'm not in an enclosed environment that can't expand, but there's a point when I can have too many. Okay, I can't put any more fish in there. Think of like a per capita thing. Does everybody see it? This is what is called logistic growth. You've heard the term logistic, but when I talk about we're going to do something, we have to figure out the logistics. That's a completely different word. Logistic growth means it's based on a logarithm. That's this version of logistic growth.
So this isn't exponential growth, right?
Well, there will be exponential in there somewhere, but it's more logarithmic. But if it's logarithmic, are there exponentials somehow? Yeah, it's all attached. When is this growth? By the way, this is also the spread of the rumor. I'm the only one who knows it. Nobody knows it. You're going to spread faster and faster and faster and faster, and then eventually almost everybody knows it. It's going to slow way down. When is it growing its fastest? When about half the people know. Why? Because half the people are spreading it. Yeah, what about when 90% of the people know? Well, I might tell you, I already know. It's slowing down. I haven't found anybody who doesn't know for a while. That's why it peaks out. Okay, so understand that that's the nature of things. We're going to come up with an equation that makes sense. So, let's say there are n people in an enclosed environment. Again, environment. Now, where in your life have you ever been in this kind of situation where nobody can come and go? Pretty easy. Look up. Can you think of an environment where nobody can come and go for a few hours?
Jail.
Well, heaven, true, yeah. Or an airplane, maybe that would be good.
The car, maybe.
Heaven, I'm pretty sure, yeah, you're not coming and going. An airplane. So this is terrible, but I know people this happened to in the last few years. They got on board an airplane and they said it wasn't an airplane, it was a gigantic flying petri dish. Because every person was coughing and spewing and oozing, and literally every person on the plane had COVID. Quite literally. And what are you going to do? Not much. Because nobody can come, nobody can go. That would be a classic environment. You're going to a game, right? And yes, technically you could come and go, but people aren't leaving a game. You're going to a big sporting event, you paid a lot of money. Right? You're probably not leaving at halftime kind of thing. So it's the same sort of idea. You have people in an enclosed environment for a finite period of time. Okay? One person enters the environment. with a rumor, I like it this way, that they cannot contain. Is that much different than I walk in thoroughly contagious, but I cannot possibly contain the germs from you? Yeah, same thing, right? If I'm coughing and sneezing and spewing, I'm not containing it very well. I have a rumor I have to tell people. Okay, so let's say that y of t is the number of people who know the rumor. Not who've been told the rumor, there's two different things. Who actually know the rumor, okay, at time t. Or let's say, how do you want to measure our time? Probably not years. Probably minutes, yeah, after t minutes. Now, I'm the only person who knows the rumor, so at time 0, how many people know the rumor? 1. So y of 0 has to be 1. That's kind of important. If y of 0 is 0, we have a problem. So y of 0 ought to be 1. I haven't told anybody yet, but I do know the rumor. How many people don't know the rumor right now? N. Now, if y is the number of people who know the rumor at any given time, so at any given time, then how many people, at any moment in time, how many people do not know the rumor?
N minus 1?
N minus y don't know. How's that? So at the beginning, y of the, n plus 1 minus y, sorry. Why? Because at time 0, one person knows the rumor. So n people do not. Because remember, altogether, if there's n people and I walk in, aren't there now n plus 1 people overall? So n people don't know, so how many know? Well, y know, okay. So the spread of the rumor, the rate of change of the number of people who know must be a scalar multiple of n plus 1 minus y. I'll put the y in front. Does that look about right? Yeah, I think that's right.
Just by like the nature of growth, differential equation, it's always k times.
Well, I don't, k has to be determined,
Yeah.
but we talked about this the other day. When nobody knows, it's not spreading very fast. When almost everybody knows, it's not spreading very fast. So when one of these quantities, when y is close to n, that means almost everybody knows, there's hardly anybody left. When y is close to 0, hardly anybody knows and everybody's left, but either way, it's spreading slowly. The rate of change, or the rate of the number of people who know, right, that's going to only speed up over time, but k is a constant that has to be determined. Now, how do I determine k? It's easy. After 10 minutes, this is how many people know. Or after 1 hour, this is how many people know. Remember I said we're going to make a simple assumption that you're not sprinting from person to person and then slowing down and taking a nap. You're telling people roughly the same rate. That's not an unreasonable assumption. So in 10 minutes, if a certain number of people know, then we can figure out the k. That's how we figure out the k, is I must give you a reading in the future. Remember Newton's law of cooling? Same thing. It's sometime in the future, how hot was it? That allowed me to calculate the value of k. This only allows me to set up the differential equation. I can't solve anything yet. So I'm going to give you information at some point. But I'd like to know, how do I do the calculus? I stated the differential equation. That was easy. I need to solve it now.
So this expression does not include the person who knows the rumor and is about to spread that
The person who
rumor?
knows the rumor, there's only one person at time 0 who knows it.
Right, so at time equals 1, you're saying y...
No, at time equals
Oh, sorry,
0.
time equals 0, there's one person, so then you just get n in that expression?
So
And
at time 0, right when we start the problem, exactly one person knows it, and n people don't know it. Because it'd be n plus 1 minus 1 at time 0.
I thought n was the number of people in the enclosed environment, not the people
And
who
none of
don't
them know it yet.
Oh, okay. So n is also the number of people who do not know the
No.
N is the number
No.
of people before the person
Bef-
walked in with the rumor.
This is how many people don't know it. Y is changing. Y isn't a constant. Y is changing. But at time 0, before anything has happened, only one person, me. I haven't even walked into the building yet.
Okay.
So there are n people that don't know it. And this would be 1 minus 1. So there's n people that don't know it. But as y increases, the number of people who don't know it is going down, down, down. When is this quantity going to approach?
0.
0. Will it ever reach 0?
No.
This is a tricky one. This is a tricky one. When we do the calculations, we're going to say there's a point when there's, let's say there's 5,000 people. We just calculated 4,999.97 people. This is people. So it's probably okay to round up at some point because you can't have a half a person knows it. Okay? The difference is people are a discrete count. If I'm asking something like a measurement, like time or a distance, no, that can have an infinite number of decimals. But if I'm talking about people, in that case, we actually would probably round out. So at what point would we reach, that last half a person? We could actually come up with a finite amount. But it's really, I want you to think of it to be safe, it's more of a limiting thing. The limit would be that upper limit. That's not important for solving, though.
So it also depends on what we're solving for, because if we're talking about people, then you can round up. But if it's the percentage of the bacteria.
No, yeah, because then that's a measurement. I can give as many decimals as I want. I always remind people that we sometimes forget all measurements are continuous. All measurements have an infinite number of decimal places. It's not actually possible to be exactly 6 feet tall. It's not possible. Because that means from a decimal standpoint, you're 6 feet point and an infinite number of zeros. That's a 1 out of infinity possibility. No, but anybody between 5'11 and a half and 6 foot and a half will call 6 foot. We report it as discrete, but it's a measurement. If I ask you your age, if you don't mind, how old are you?
31.
So your birthday was today. His birthday is today. In fact, it was at 1:18 in the afternoon. Or is that probably not true? Oh, you know what? You forgot to give me the decimals. Does anybody give me decimals when I ask them their age? No. If you're 9.5, you say 9.5. But you don't give me and this many months and this. So in other words, you reported an integer value. Even if tomorrow was your birthday, you were still going to truncate, weren't you? Because you're doing a measurement. And by the way, you're about a minute older than when I asked you. I hate to tell you, you're one step closer to the end. It's a measurement, isn't it? Your age is a measurement, but when you report it, you're rounding it down for convenience. But your age is a continuous measurement that is actually changing at all times. Yikes. So what we report, we have to round up. We report a discrete value, but we're doing a continuous calculation. So that's why I said in the case where we're saying at some point, will everybody know? Yeah, it's not like we got one person left, but according to the mathematics, we're never going to have that person. So if we all live forever, that person's still never going to completely know. No. There's people. We have to have a whole person at some point. Okay, let's set this up to solve it, because I want to solve this in this form rather than the specific numbers, because that way we can come up with a formula. And if we come up with a formula, then we'll work for all problems. If I give you the numbers now, you've only been able to solve that problem. You'd much rather do it in a formula sense. You guys remember doing quadratic formula in high school? Yeah, and you used it as a method of solving quadratics by completing the square. That's how it started, and then you said, let's do this generic, ax squared plus bx plus c, we'll complete this square solve, and we got this beautiful formula, and then you practice and practice, and you knew it inside out. It was a piece of cake. But nobody remembers the quadratic formula with specific values, right? No, you learn it A, B, C, so you know where they go in the formula. You can't learn a formula with specific values. That'd be like the equation of a line, y equal mx plus b. No, I can only do y equal 2x plus 4. That's the only line I can do, with specific numbers. It doesn't really work. So how do I set this up? Is this separable? Yeah, because n is a constant. So can I do 1 over y, n plus 1 minus y, dy equals k dt? Stare at that for a moment.
Yes.
So therefore, well, I'll do the one on the right. You guys okay with the one on the left? Is that a big yuck? Well, isn't that the one we just did a moment ago? Didn't we just do that problem or a version of that problem? Yeah, it's two linear factors. It's a partial fractions decomposition. But it's two linear factors. That's, of all the partial fractions that exist, that is the friendliest one. Two linear factors, not 5. Now, the coefficients are going to be horrible. I'm not worried about that. That doesn't bother me. So 1 over y, n plus 1 minus y equals a over y plus b over n plus 1 minus y. Okay? So, when I put everything over a common denominator and then I equate coefficients, the next thing I'm going to write is 1 equals,
A times m plus 1 minus y. B times 1.
everybody good with that?
Huh.
That's not too bad. All right, how about if I start with y as 0? Then what do I got? Oops, sorry. Should write y equals 0 first, sorry. Then I've got 1 equals
A m plus
a times n plus 1, which means that a equals 1 over n plus 1. I want this to be 0, so what should y equal?
n plus 1.
Just n plus 1. Don't overthink it. N plus 1 minus something. N plus 1. So then the left side is now 0, and the right side is, oops, the right side is what? I wrote this, did I write this correctly?
B times n plus 1.
Y is n plus 1, make sure I didn't screw this up, okay. And so that means that
It's the same.
let's do a quick check. What is the most common mistake, do you think, in a partial fractions decomposition? Is it the wrong numbers?
Signs.
Minus
Probably
signs.
the wrong signs. And we did everything right, but we lost a sign somewhere. So I'm going to check it. Here's what I'm going to do. A and B are constants. So could I rewrite this as 1 over n plus 1 times 1 over y plus 1 over n plus 1 minus y? Would that be legal to write like that?
Yes.
Yeah, I'm lazy. It makes my check a lot easier. Okay, if I put this over a common denominator, that's going to be n plus 1 minus y plus y over y times n plus 1 minus y, which is that, cancels, and then that cancels, and I'm, good thing? Yeah, we did it right. Everything canceled. But I would still check. If I have specific numbers here, the check is the same. So, going back to here, we now have this is equal to, and by the way, I'm going to put the n plus 1 on the outside. We tend to stare at a constant, especially if my numerator's ugly. We tend to stare at the constant like it has something to do with the antiderivative. No, it's just multiply. So pull the n plus 1 out of the problem altogether, so it's not in the way. And because they were both n plus 1s on the bottom, I'm going to have 1s on the top. I like that.
Why do we pull out the n plus?
Oh, just to, because it's a coefficient. You don't really want to put that fraction in the numerator, do you? It's just, it wouldn't be wrong. It's confusing because all of a sudden it looks important when it's just a coefficient.
If it had a y in it though, then we.
Oh, no, I can't pull variables out, but
Okay.
remember, you're finding a and b, which are just numbers. There was no y's here. Now, I'm going to erase a little bit of this so I can squish this in here, okay? Can we integrate this?
ln of y minus ln of n plus 1 minus y. There should be a minus. Yeah, there's a
Think of a u sub. If my u is n plus 1 minus y, then my du is negative 1 dy. Yeah, that's a place that will get us. That's got to be a minus. Because the derivative of this would have a chain rule factor of negative 1. Okay, and then the right side is what?
KT plus C.
KT plus C1. Good. And by the way, we will easily be able to find the value of C. That won't be hard at all. Remember, because y of 0 is 1. Now, this came up earlier today when we were talking about how do I get stuff out of here. When you have two logs, which is really common, always squish them together as one first. You're going to exponentiate, but you do not want to exponentiate separate. the algebra is too messy and what to do with the constant gets confused. No, these are already together, that makes it easy. So if I squish this together, it's gonna be log of what? Y over n plus 1 minus y. Now, I know it's an absolute value. What does y represent?
Number of people.
Number of people who know n plus 1 minus y is the number of people who don't know, and those are both strictly positive. So can I drop the absolute value?
Yes.
In the long run, do you think it's going to matter? No. But if I can drop it and I know, then later it sometimes feels like we're cheating, doesn't it? When you have an absolute value exponentiate and it somehow miraculously goes away, it's usually because it was strictly positive in the first place. I'm going to drop it because you just told me numerator and denominator are always positive. How about if I multiply the right side by n plus 1 for now? So far, so good? I could find the value of c now. I could exponentiate both sides, manipulate that, and then find the value of c. Then it actually does not matter. What do you guys want to do?
Just, plug in, find seeds.
The thing on the left is kind of creepy looking.
Yeah.
Meaning at time 0, y is 1. So I'm going to have 1 over something is a fraction within the logarithm. I don't know that I want to find c. I think I might want to exponentiate. I think I might want to get rid of that. So now what does y over n plus 1 minus y equal? We're going to be doing some algebra that you may never have seen before. And it's not comfortable necessarily. Well, n plus 1 is a constant, correct? K is an unknown constant.
C is another.
C is a constant. God, I have constant. N is known. K and C are not. C is going to come from an initial condition. K is going to come from me reading something down the road in the future. N is a constant, so don't mess around. The n minus 1 is not a problem. So what am I going to have now? I'm going to have e to the, and I'll just leave it like this for now, n plus 1 times kt.
E to the, oh, C.
How about if I write it as e to the n plus 1 times c1? Because that is still a constant. That's not a constant, but that is still a constant. And again, if you want, you can now call it c2. N plus 1 is given. I know it looks confusing. If I said there's 5,000 people in this building, then right now you have a 5,001 right there. It's never going to look like n plus 1, right, when I'm doing it. I'm going to have a specific number right there. I would really like to write y equals. This is not very friendly. There's a very low-level algebra step that's going to take place next, but it may be something that you really haven't done before. I know I do a problem maybe in Calc 1, maybe another problem in Calc 2, where something like this will come up. And here's what I mean. I want you to, I'm going to do it really simple. Really simple. I've got 2y over 3y minus 1 equals 6. And I want to solve for 1. How the heck could I do that? Well, how about if I go like this first? Did that work? So what do you think I'm going to do here?
Wait.
Multiply both sides, gather y terms, factor out the coefficients. That's the only way to do it. It's not high-level algebra, but it's an algebraic step you may never have seen before. I have a quotient where numerator and denominator both contain the same variable, and I need to isolate the variable. This is exactly how you do it. You don't have to be clever. So I said, well, let's multiply both sides and then gather y's. Now, I'm lazier than you. That's not going anywhere. I just don't want to keep rewriting that over and over again. So that stuff on the right, let's call it stuff, and let's indicate stuff with a big S. So now what do I want to do? This over this equals big S. Does that now look like the problem I just did here?
Yes.
Yeah, it's exactly the same problem. So y equals stuff times n plus 1 minus y. We're actually almost there, by the way. So what's that? That's stuff times n plus 1. Remember, n plus 1 is a coefficient. You could write it on either side, doesn't matter. Minus stuff times y. Now, send that to the other side. Yes, my ways may be unconventional, but they definitely work. So now what do I have on the left? I have 1 plus stuff times y equals, if you will, n plus 1 times stuff. So finally, y equals n plus 1 times stuff divided by 1 plus stuff. If I could, I would, but I can't, so I won't. You want to cancel real bad, don't you? No, but there is something we are going to do a little later. Now, what am I going to do? I'm going to go back and put this in for stuff. Because at some point we're going to need it. Okay? So we now have a form. Have I solved the problem? Well, not exactly, because I still have a K and I still have a C. Now would probably be a really good time to use the initial condition, because now I can replace y with 1. Everybody got that? So now if we do our initial condition, so let me go way, I'm not going to write on that board. I'll do it over. I'll do it over here. I hate erasing my work, but I don't see any other way. So now let's write formally what we actually have. We have y of t equals n plus 1, and stuff is c2e to the n plus 1 kt over 1 plus c2e to the n plus 1 kt. Did I leave anything out? Help me out here. No boo-boos. All right, we can now find the initial condition. Y of 0 equals 1. Now replace t with 0. Ooh, I like that. That whole thing becomes 1, doesn't it? So my numerator becomes n plus 1 times c2, and my denominator becomes
1 plus C2.
1 plus c2. Kind of has the same feel again, don't I? Have to manipulate to get the c2 by itself. But I'm going to have a very specific value now for c2. It won't be unknown anymore. The k is the thing I'm least worried about. Because I'm going to say, okay, in 10 minutes, this many people know, and you're going to be able to solve for k really fast. Why will I be able to do that fast? We're going to know c2 in just a moment. This is a constant, but you know, we're about to know this one, we're about to know this one, we're about to know this, we'll know this one. This is the only unknown left in the problem. If I now said, in this many minutes, this many people know, k will be the only thing left to solve for. And we will be able to physically plug in the numbers and see what k is. That one I'm the least worried about. We're going to do it. Don't worry about that. Okay? So, can we isolate the c2 now? Again, same thing again. It's math you may never have seen before, but you know it will work, and now you see a reason why you have to do it. The thing I'm looking for is on top and bottom. That's a 1. That makes this easy, doesn't it? So on the left side, if I multiply through, I have 1 plus c2. On the right, I have n plus 1 times c2. I want all the c2s together. So how about I send this one packing? How about if I write this one as nc2 plus c2? Oh, then that's all I really have to do, don't I? Do we know what c2 is then? After all of that? 1 over n. That wasn't as bad as you thought it was going to be. You thought it was going to be something log-ish or something, huh? So far, so good? So we can go one step further. C2 is 1 over n. Here. So now I have, how about if I write that as n plus 1 over n, e to the n plus 1 kt over 1 plus 1 over n. Now, I don't like that. Can I multiply numerator and denominator by n? Now I have on top n plus 1 e to the n plus 1 kt, and on the bottom I have n plus e to the n plus 1 kt. Huh. Again, I can't cancel anything. Now, this is not the usual form of the final answer. I don't know if the author actually took this one to its completion. Does he or does he not? Or she? He. No, he's a he. Sorry. Now, everything I said is true. Everything I said is correct. And if I've got to evaluate this, I have 2 places I got to deal with that e. I'm lazy. I'd rather not deal with e twice. Is there a way I can only have to deal with e once?
Multiply top and bottom by e to the negative.
Perfect. If I multiply top and bottom by the reciprocal of this, it will go here, it will go away here, it will be added to here. But it will be less work. And that's kind of the usual form, and there's a reason for that. If I multiply it by the one with the negative exponent, then it will approach 0 on a limiting effect. Right now, these are both going to grow without bound, aren't they? Which makes finding limits a little bit trickier. It just makes it's a little bit trickier to find the limit. So the last thing I'm going to do with manipulation, which I think is a really cool step, we're going to multiply top and bottom by this. And now we're going to have the final form that we're usually going to deal with. That's just going to be a 1, isn't it? Now, at time 0, how many people know the rumor? At time 0, how many people know the rumor? 1. If I replace t with 0, then this is n times 1. I have n plus 1 over n plus 1, which is 1. Or more like, okay. As t grows without bound, what is happening to this quantity right here?
Getting small.
So it's approaching, in fact, it's approaching 0 pretty rapidly. What is the limit of this as t grows without bound? This is approaching 0.
The number.
N plus 1 over 1, which is n plus 1. Isn't that how many people are now physically in the building? Is n plus 1? Me plus the n people who just didn't know what was going on? The n sacrificial, no. Is that a good thing? Yes, that's a really powerful thing. You like this so far? There's a lot of arithmetic. The only calculus, literally the only calculus we did, we integrated 2 terms that gave us natural logs. That was easy. We had to do some partial fractions decomposition on that. So I have just shown you the governing equation that is always true. This is the logistic equation for population. I'm sorry, not population. Spread of a rumor, spread of a virus in a closed environment. That is important because if we're an open environment, the rules aren't the same. Why in an open environment does this change? There's one really simple part of this that changes.
And changes.
Transitional condition.
There's not going to be a fixed number of people. You're moving around the community, n's never constant, is it? It's not the fact that it's open air. It's the fact that n is never constant, so I can't use it in the equation. So let's say you left the building and now you walked out to the beach. I mean, there's 10 times as many people, but people are coming and going. That's the other thing. So this works in that context. Now, how do I find k? Remember I said k would be, well, okay, it's not trivial to find it. It does live in an exponent, so it's not the easiest thing. But can we find k? Yes. Yeah. Give me a future, y of 10, y of 50, y of 100. I will give you a specific value. I'm going to replace t with that time. This will equal a constant, then I work backwards and solve for k, which is not the easiest thing. It's kind of messy. We're going to do that in a moment.
So the K is just related to how fast or slow.
Some people call it the
spread.
proportionality constant. It's the constant that determines the speed that it's growing. Now remember, when we took the hot cup of coffee and we set it down, if I put the hot cup of coffee in a humongous salad bowl, or I put the hot cup of coffee in a well-insulated thermos, is it going to read the same temperature in 10 minutes?
No.
No. So I needed that future reading to determine how fast it was slowing down. It could slow down really fast, and it's really open, or slow down really slow. I have no idea. I used the future reading. I have no idea how fast this rumor is spreading until I measure some fixed point in the future. And now I can tell you exactly what the K is, which then means if I said in 10 minutes, here's how many people know. How many people are going to know in an hour? How many people are going to know in a day? How long before this many people know? I can now ask all these questions, assuming that we are spreading it at a relatively constant rate, which, by the way, is not an unreasonable spread. See, think about the spread of the virus. I'm coughing on you all. I don't like run up to you and cough and then slowly walk to you to cough. I'm probably coughing at a constant rate. You see what I mean? That's why that's not an unreasonable assumption. Is it absolute science? No, but it's the best we can do in terms of modeling. This is called a mathematical model. It's not perfect, it's not flawless. This is how we do things in real life. We say, based on this model, we can use this as a predictor. Is it absolutely perfect? No, but if I am able to do certain things, measure you in the future, and then maybe even make another measurement in the future to see if that K basically held, now I can use that to combat. You see, you're the Center for Disease Control and you have this virus isolated in a certain community, and you can talk about, okay, we can combat the spread by this. I mean, think about certain cities. Didn't certain cities close themselves during COVID? Why? So you couldn't take the virus with you. Good or bad, live or die, you couldn't take it with you and spread it. So in other words, this model actually fit perfectly if I close off the city. Now, the city's awfully big, there's a lot of people, but I don't know about you guys, but I watched every single day. I read everything the CDC put out for the first year. I looked at the statistics. I looked at New York City a lot because that seemed to be the worst place on earth for a while. And they say this many people, and then it started to plateau. And then even though we had tons and tons of new cases every day, the number of new cases started going down. Why did the number of new cases start going down? Were people more responsible? No, there were just fewer people left who hadn't gotten sick. You realize it's the same thing that eventually would happen. It almost completely dropped off. So we actually do use this. It's not absolute perfect science, but it is as good as we can get knowing what we know. You guys cool with that? Now let's do a specific problem. Same problem. All right. Let's have some fun. There's 50,000 people. You're at a football stadium. Okay? In 10 minutes, let's say 50 people know the rumor. By the way, that's ridiculously fast growth. But we'll go with that. In 10 minutes, 50 people know. I can't help myself. I told you, because I'm so excited, but you know what happened? You got totally excited, and then you got so excited, so in 10 minutes, 50 people knowing. That's not outrageous considering how fast everybody wants to tell it. Maybe I'm telling someone every 30 seconds, in other words, or once a minute. Heck, once a minute, it'd be more than 50. Because you remember, I'm doubling and doubling and doubling and doubling. Okay, so here's what I'd like to know. First question is, tell me y of t. Secondly, how many in 30 minutes? That seem reasonable? Well, obviously, 3 times as long, it should be 150, right? Right? 150? 3 times as many people? Or do you think it's more?
A little more.
Probably a little more. Probably a lot more, yeah. Somebody asked a question, exponential growth. Is this exponential growth? Not exactly. You see exponents in the problem, but you see them in numerator and denominator. And so the fact that you see them in both, they kind of have a canceling effect. In fact, when I put it this way, now you can see, oh, this exponent's now making the whole thing approach something. Remember my picture? Fish in the stream. Now do you see why it's leveling out? That upper limit is that n plus 1, and the bottom limit was the start. So this follows suit with what I showed you earlier very closely. So let's start the problem, I don't know, how about here? You okay with starting here? I am. I don't have the energy to do all this again. This is taxing. You know, I want to take a nap now. You know? I'm glad I only have to do this once a semester. I don't love the algebra of this problem. I love this problem because it's such a powerful thing that we can control this. But the actual physical doing it, it's icky, right? It's not the friendliest math. So what about right now? Y of t is
50,001.
50,001 over 50,000 e to the negative 50,001 kt plus 1. Do you think the plus 1 is important? I mean, is it going to be life or death if I drop the plus 1, boy, that makes this a lot easier. But the problem is the limiting effect won't work exactly the same. My numbers aren't going to be hugely off, but remember, as t gets big, this is approaching 0 very fast. Oh, so that plus 1, let's say this is a small decimal. That plus 1 kind of hugely changes that quotient, doesn't it? That plus 1 actually is very important. The bigger t is, the more impact that plus 1 has. Because the bottom's approaching 1. If I don't have the plus 1, then the bottom's approaching 0. Ooh, that changes things, doesn't it? So, now what? I have it somewhere in there. Y of 10 equals 50. Okay, y of 10, which is 50,001 over 50,000 e to the what?
Negative 50.
That's going to be negative, I need another 0. I just replaced t with 10. Everybody got it? If I don't do that, I'm going to have a boo-boo there.
And that whole thing equals 50, right?
And then this whole thing equals 50. Now, be lazy. The thing I want's in the denominator.
Don't you have like one more extra 0 on the 5,000, or it should be like 50,000?
Need another 1.
Did I lose a 0?
No, I think you put an extra 0, I think, because it's supposed to be 5,001, but you have,
No, it's 50,001.
oh, okay, got
That's
it.
50,001, and now I'm multiplying it by 10.
Oh, okay.
So now it's 500,000 in 10. Yeah, no, there should, yeah, just, be careful. You can always fix it later if it doesn't look right. Now, how do I do this? Flip them both over. So now I have 50,000 E plus 1 over 5,001 equals 1 over 50. So just move that up to here now. See how I did that? Pretty lazy. Plus 1. Okay, so now I have 50,000 E equals 50,001 over 50 minus 1. 50,001 over 50 minus 1. Don't think decimal yet. Because remember, I'm going to be multiplying both sides by the reciprocal of this also. If it's a terminating decimal, could I use a decimal here? If it's not, should I? Remember, you're solving something in an exponent. The last thing you want to do is decimal round off errors. So you can always leave things as a fraction. This is going to be kind of nasty. Yeah, question?
Oh, wait, I was gonna say where you got the minus 1 from, but you just moved it after you multiplied.
Yeah, because I got to get that guy out of there. And in fact, let's go one step further. E to the negative 50,000. This is something I would kind of leave to you. Here's what I have on the right side. I haven't done anything yet. I don't mind writing that as a fraction. I have no problem. And if that is a terminating decimal, I don't have any problem with that. But if that's not a terminating decimal, you've got to be really careful. You don't want to round off, you just leave things as a fraction. First of all, as a fraction, it's going to have a really big denominator, right? It's going to be 2.5 million. So maybe you don't want to write it as a fraction. So tell me what, this is a terminating decimal, so what would this be? Let's all calculate that. Again, it does, as long as you're not rounding, you're totally okay writing a decimal. But because of the nature of the problem, I think you want to be really careful about rounding.
Stop.
I'll do my part.
0199804.
That will reduce significantly. Now, this is kind of a personal choice. This is not K. This is what this equals. K is going to be a logarithm. So you know this is going to show up probably as an exponent or something. So I think in the textbook when they do this, no, I think the author left it in decimal form. That's a terminating decimal, so it's not the worst case. But because K is going to be a logarithm, now it really gets messy, doesn't it? So I can leave it like that, or I can go 199804. 1, 2, 3, 1, 2, 3, 4, 5, 6. Oh, that didn't help. Now, I'll leave it like that. Okay. So now, I need a different color because we're going to run out of room. Sorry. I'm so afraid to erase things. Where's our actual equation? It's right here. Okay. I'll erase this stuff there. I just don't want to lose our actual equation. So now I've got negative this K, is that right? Negative this K equals ln 0. By the way, you can write that as a fraction. That is not incorrect. But it's just, it's a ginormous denominator, so I'm not sure how useful it is.
Just denote it as stuff and we're done.
Exactly.
Just denoted as stuff?
Yeah, and then we're done.
Yeah, the problem is I'm going to have too many stuffs, though. So therefore, K is. Now, if I start like this, I think that's correct. Is that correct?
That looks pretty good.
Yep. Okay. Now that is awful. That's what K is.
That's okay, K is in the exponent.
But K is in an exponent. And not only is K in an exponent, what's the first thing K is getting multiplied by? Well, exactly 1/10 of this. Oh, so yes, you can calculate this as a decimal, but I'd rather not. I'd rather leave it. Can we manipulate this? This is K. How big is K? I have the slightest idea. Let's calculate. It's probably really small. 0199. Do we all agree on that number? Is that, everybody double check that that number is actually correct? No, I was relying on Benito, and that's, he told me to, bet on the Niners. Anyway, so. Yeah, we all know how that ended up. So that number is really small. Right? It's on the order of 10 to the negative 6th power, but it also does show up in an exponent, so I'm less worried about that part. By the way, it's really small, but it shows up in an exponent in the denominator, which now makes it actually big. Yeah. Okay, so we all know what we want to do. Let's see if it's clean. If I take that K and I put it right here, then I have e to the
1/10, negative 1/10.
Yeah, let's just go ahead and cancel those. So yeah, so e to the negative 1/10 times the log. I would much prefer to do it this way because, what does this equal? Is that, oh wait, is that still negative? It's still, yes, it's still negative.
Oh, sorry, it's negative here and here, so it becomes positive.
Well, no, the value, this value is a positive number.
Oh,
Oh, because the log is negative.
Because this value is a positive number, but it's ridiculously small. Okay? But again, like I said, but it's showing up in the denominator, and then it's got the negative. So at this point, we have, okay?
Wait, no, but this was our value for K, and it has negative.
Oh, I'm sorry, I did,
Yeah.
thank you, I didn't see that. This should be a positive one, thank you. Yeah, I didn't, so you're right. This should look like this, and what is this now? It is this to the 1/10th power. Times t. Does this look familiar? I read it as t over 10. Does that look like stuff we've done already?
Yeah.
Yeah, and here's the beauty. I said in 10 minutes. So if you wanted to check it, you'd put a 10 in there and you'd get exactly this value and it would work perfectly. This is a good thing. We have just improved on our answer, I think. I could be wrong. Improvement, I guess, is in the eye of the beholder or something like that. All right, final run through. 50,001. 50,000, and I'm going to replace the E with this. Yeah, did I do something?
Yeah, I just have a question.
Sure.
On equations, do you want us to rederive these equations?
No.
Should we just start with?
Oh, heck no. Yes. No. No, don't do that. It takes too long. You might go sideways at some point. Yeah, good.
I missed where the 1 time came from.
I'm sorry, where the...
The 1 time.
Oh, this is K. Look at my denominator. I am multiplying that by 50,001. My denominator is exactly 10 times 50,001. Why? Because that's, remember, we plugged in the T10. That's where I came from. So I believe we are going to check this, guys. We will have a way of checking this. Not that anything could possibly go wrong. So I'm replacing E with this. Plus 1. Now, get out your calculators. If T is, we're going to do a quick double check. If T is 0 times 0, then that's 1. Then it's 50,000 plus 1. This whole thing is 1. As T grows without bound, this is approaching 0. Why? Because this number is between 0 and 1, and I'm raising it to a large power. It's going to 0 really fast, actually. Which means that it's approaching 50,001 over 1, which, like we said before, that's my whole crowd. That's a very good thing. And now the last check, and this is just as important as the first two. We used an initial condition. It better still be true. If I replace T with 10, now let's do that calculation. By the way, be lazy. Calculate your denominator. Calculate your denominator first. I can do the whole thing. Well, just use your parentheses key, okay? So I have 50,001 divided by parentheses. 50,000 times just this, because we're replacing T with a 10. 0.0199804 plus 1. Close that, and my calculator says 50. Now we can dance in the streets. That's perfect. How many different versions of this do you think we could actually sedate? Many. This is my favorite because at no point did I round off. I don't have any logs. I don't have any exponentials. In other words, from a calculation standpoint, that one's going to be a lot easier. Now, if I say how long until the following happens, we still hate that question because that means you still have to solve for T. It's still logarithm. That problem is never short and sweet. Not that one. But my follow-up question wasn't how long before everybody knows. No, my follow-up question was 30 minutes. So you're going to do the same thing, but now you're going to cube this. Okay? So let's do that. In 30 minutes, we'd like to know how many people have been turned to zombies. I think that's kind of what this is all about, right? A lot of people are now zombies, yes. 0.0199804 T plus 1.
I got 25 gig. Yeah.
You got did Did you get this?
Yes, I rounded up.
Now, because we are talking about people, this would be safe to go ahead and say 745. Do you agree? Is that a lot? I have 50,000. Now, you understand this. By the way, this is actually a legitimate problem. CDC deals with stuff like this. We have one person walk into a stadium of 50,000 people. One person. In 10 minutes, 50 people know. Well, is that fast? Well, let's see, 20 minutes later, over 35,000 people know. Yeah. Because every person I tell is telling somebody it's doubling, kind of at light speed here. And again, I will go back to the scariest movie maybe ever made, Outbreak. You guys have all seen Outbreak? How many have seen Outbreak? You remember the map when the Defense Department is showing the map of the United States and saying, here's the small town today, and they project it was either 48 hours or 36 hours in the future, and it was the entire United States was now dead. The entire country was wiped out in hours, not years or months or days, based on the spread and how fast the virus was growing in the small community. That's terrifying. By the way, how the heck did they figure exactly verbatim the same map? There's nothing different about what they did than we did. Why? Because they had an enclosed environment. They could absolutely model how fast it spread. And now if we take it and make it an unclosed environment, assuming you're not all running for your lives constantly over the next couple of days, avoiding the zombies that are after you. That's what I'm saying. That's the scariest movie because how fast it actually spread mathematically based on the model we just did. But we're not talking about it. We're talking about rumors, But, keep your rumors under control, obviously, because one rumor to stadium, look at this, It's terrible, terrible. Any question on this? This is kind of cool stuff, huh? Now, you're saying this was such hard math today. No, this was very tedious. We did one integral and it wasn't all that hard, but it was all the in-between solving. This is not stuff you've done before. Logistic growth is not the friendliest algebra, but in the end we got something that this now serves as a model. Now, how would I make this number change drastically? If I raise that or lower that, it would change that one, and that's really all that comes down to. You didn't have any control over that. You just calculated what it would be based on this. You good? All right, let's go ahead and stop that.